Okay, so we've seen the soil water characteristic curve, and we have this main draining curve and main wetting curve. And that's how water is retained in soil. But how does water move through soil? Water moves through soil due to hydraulic conductivity, or we characterize it by hydraulic conductivity. And we're going to use the letter K for hydraulic conductivity. And on the bottom axis, we're once again going to use the symbol theta for the soil moisture content. And that's the volumetric moisture content. And what we're going to see is that when we are at the saturated value, right here, then the conductivity will be maximum. Then all of our pores are filled with water, and so it has the maximum possible surface through which water can flow. And we will call that the saturated conductivity. Interestingly, remember here in the characteristic curve, when we drained it, it didn't go all the way to zero. We had this thing called the residual water content. Now, the residual water content means that that's when the films of water are no longer connected. So similarly here, on this axis, at theta residual, the conductivity will be zero. Okay? So we're going to draw a line then showing that the conductivity decreases, the hydraulic conductivity decreases as the soil dries. Now you might have asked, hey, wait a minute, why is this not a straight line? And there's a lot of reasons why it's not a straight line. Number one, when we started with our soil, we had our particles in our soil, and it was saturated with water so that the water could actually flow everywhere. And it could find the easiest route for passage through our soil. However, when we drain our soil, and now there's only water left in little films, little kind of capsule, corpuscles and films, then the water has to flow in much more tortuous paths. And it doesn't get this path at all. So this path is completely gone, and now the new path for water to flow will be along this much more tortuous path, along this little thin film, and maybe like that. So what we have then are several factors which decrease the hydraulic conductivity. Number one, the paths are longer. Number two, there's less cross-sectional area. Through which water can flow. And number three, and this is really important, the paths are thinner. So that the water is going through thinner paths. It turns out that if this is a pore through which water is flowing, the ease of which water going through that is proportional to its radius to the fourth power. So as we go to smaller and smaller pores, the resistance to flow of water goes up with the fourth power. So just for example, if we had a pore that went from 1 millimeter typical pore size to 0.1 millimeter, just having smaller pores, that suggests the resistance to flow through any given pore would be 10,000 times smaller. 10,000 times smaller, that's for any given pore. The good news about having small pores is you get more of them in a particular unit area. So in fact, you can get r squared more pores that are smaller. And so in fact, if you had a media that went from 1 millimeter pore size and you had another media that had 1/10 of a millimeter pore size, the actual conductivity would be 100 times smaller. Because each pore will be 1/10,000th as permeable, but there'd be 100 times more pores, and so we get 100 times lower permeability. So as we go to thinner and thinner films of flow, the resistance goes up because those paths are made up of thinner films of water, and it has a tremendous impact on the permeability. Also, the cross-sectional area through which the water flows, a lot of our cross-section is now gone because it's drained out. And finally, the paths are longer, so it takes the same amount of potential energy stretched over a longer path, means slower flow. So all of those things give rise to a conductivity curve which dramatically drops as we deviate from saturated soil.